All right, yeah. So we're back with project number 2. We're doing 2D flow over a flat plate, laminar flow. So we're going to be doing it in Ansys again. So we're going to open up Workbench and we're going to wait for this to load. And we're going to be using Fluent again. First, going to do the geometry. So I'm just waiting for this to load and I'm opening everything up for you guys. We have everything in. So we're doing fluid flow, Fluent. We're going to do the geometry first and we're going to do new design model. So as you guys saw here, our constraint is that it has to be a 100 centimeter long flat plate. So it's kicked me out. But yeah, so we're going to jump right in. We're going to do normal, XY. We're going to do this quick. This is fairly easy. All right, so we have a rectangle. We're going to dimension it. I'm going to change the units to centimeters just to get everything, just keep it easy. But later on, we'll just deal with any conversions to meters because we'll have to do some conversions to meters. So we're doing 100 centimeters and I'm going to do 50. All right. Yeah. So that's how I want it. Let me zoom in real quick. I'm wailing the math for. All right. And then we're going to do concept. We're going to do surface from sketch. We're going to hit a piece of it, hit apply and generate it. So this is how we're looking here. And as you can see, we have our sketch here. So we're going to jump into Workbench again. We're going to do mesh. While we're waiting for the mesh to load, our goal is to have as many divisions on the bottom half of our figure because we want it to be a flat plate and we want to just simulate the flow over that flat plate. So we don't really care about anything else. Like all this extra space that we have here, we don't really care about. We really just care about this bottom section here. So we're looking to make as many divisions as possible on this bottom half here. So because of that, I'm going to show you how I chose to mesh mine. So for the mesh, you don't have to necessarily do this. You could jump right in and generate, but I like to just insert a method first, click on the plate and do apply and then generate it just so that we have our first divisions like this, but it's a simple cut. So this is how we're starting off. But obviously this is not what we're going to say. This is nearly not enough divisions on the bottom. We're going to mesh it again. We're going to insert face meshing. We're going to use the face tool. We're already on it. Sorry. And hit apply and generate. And then you can see here, a little bit more refined. And we're going to insert now and we're going to do sizing. But for this, we're going to grab the edge tool because we're going to use the top and bottom surface. So we have our top and bottom surface. We're going to hit apply. And then we're going to do element sizing. We're going to do number of divisions. For this, we're going to do 50. And then for our capture curvature, we're going to put it on no because we want our behavior to be hard. Basically, we want the computer to compute this calculation no matter what. A very hard calculation, but we want it to compute it. So now we're looking a little bit better. As you can see, towards the bottom, we have smaller cuts, but this is still not nearly as refined as we wanted. So we're going to do insert. We're going to do another sizing. We're going to have that edge tool. We're going to do the leading edge, which is essentially our inlet. And then we're going to do number of divisions. This we're going to do 60. And then here's where things get a little different. We have the capture curvature off because we're doing hard again. Or no capture curvature rather. But we're going to have a bias. So we're going to use our top bias here. And then we're going to have a bias of 70. So this basically is that it has the bottom edge or bottom surface closer to where we have this plate here at the bottom has more divisions than a top surface or free surface above. So we're going to generate that and I'm going to show you how it comes out. After we generate it, when we go to mesh, you see how it comes out. So we're going to do the same thing to the outlet or trailing edge, I should say. So we have it there. We'll do the same thing. We're just going to do it the opposite way because our bias is going to be flipped. So 60 again, no, hard, bias, 70. But we're going to do reverse because as you can see, it's flipped. Our small divisions are at the top. So we'll do reverse bias. We'll click that. We'll apply it. It's on the bottom now. We'll generate it. And we'll go to mesh and our meshing is done. We have as many small divisions as we possibly can at the bottom. As you can see, the rest of the surfaces, divisions are okay. I mean, they're not fully, linear or uniform, but it's fine. next thing that we're going to do is we're going to name our surfaces. So we're going to grab our face surface here. We're going to tap this and we're going to hit N. We're going to call this airflow. We're going to hit OK. So that's our airflow. Then we're going to grab the edge tool. We're going to do all the others, the edge surfaces. So we'll do this. This is going to be our inlet. Hit OK. We'll do this. This will be our outlet. Oop. Outlet. Outlet. There we go. And then this is going to be our plate. This is going to be our far field pressure. Sorry, can't spell, bro. Gonna be our far field pressure surface. So this is it. So we have our 5 surfaces here. Just make sure everything looks good. Plate, top. All right, cool. Pretty easy. So now we're gonna get out of our mesh and we're gonna go back to workbench. We're gonna update the mesh. I'm about to duplicate it by accident. And then we're gonna go in our setup. So for the setup, 2D, always double precision. And if your CPU is powerful enough, you have multiple cores, out up the solver processes just so it's faster. All right. Just gonna wait for this to load. So yeah, so waiting for our mesh to appear. It's taking a little minute. Basically, we're gonna run everything. And we're gonna first check and do a quality report because we want to make sure everything is looking good. As you can see in the console, it's pretty much loading everything that we had for our mesh. It's gonna tell us. And disregard this error. It says please either change the boundary condition type or enable ideal gas law. That has something to do with our far field pressure surface, which is the top surface here. So what I'm gonna do is I'm gonna hit OK here just so that I can get this damn meshes out the way. And we're gonna leave everything here, pressure based, absolute, steady, laminar, or planar, sorry. We're gonna do a check on our mesh. So our mesh check is done. It shows the volume, our min and max face area, y and x coordinates, and then we're gonna do report quality and it shows our min and max aspect ratio. So this is our mesh. Everything is good there. We're gonna first jump into models and don't worry about the error that we saw before. I'm gonna clear that up. We're gonna go to viscous and we're gonna go to laminar because we're doing laminar 2D flow. We're gonna close the models. We're gonna go to our materials and we're gonna go to fluid. And we're gonna change the properties of our fluid. So air here, we're supposed to be running it with a free stream velocity of 2 meters per second, air density of 1.2, and a viscosity of 1.8 to the -5. Sorry, so we'll go back into fluid. So we're gonna change this to 1.2, and then we'll leave that there, but we'll change and create close. So it's still giving me this error here just because anything that I change is gonna continue to trigger that until I actually fix it. We're gonna leave this open just so that we can come back to it, but we're just gonna check everything else. We're gonna go to our fluid airflow. We're just gonna make sure everything is on airflow. Close that. The solid we don't really touch, but we're gonna go to our boundary conditions. So I'm actually gonna fix this error now. It won't disappear yet, but I'm gonna tell you why it's giving me that. So if you look at our far field pressure, this is set to pressure far field, and for this constraint, this is not possible. So what we're gonna do is, well, it's not possible with our current configuration rather. So we're gonna change it to symmetry, which is basically gonna allow this to be just a flat line or a flat surface similar to our plate on the bottom, but it's still far from this flat plate. So it won't have any effect in terms of how our fluid is flowing over this flat plate surface here. So we'd apply. For inlet, we're gonna just go through all of them now. For inlet, we want to make sure it's velocity inlet, and it should pick up on that pretty easily. And we're gonna change the velocity magnitude to 2. Okay, that's what we're using for this. And then for interior airflow, it should just be interior. And there shouldn't be any issues with that. That one should be interior. All right. Sorry. And then for outlet, we want to have it be a pressure outlet. Edit this. Shouldn't have anything here. If anything, I'm gonna come back and try to do prevent reverse flow. I haven't had any problems with it yet, but so far so good. Wall. We're gonna do stationary and no slip. All right, so now we're gonna go to mesh interfaces, just make sure everything is good here, everything is fine. And then we're gonna go to our reference values and we're gonna go to the inlet just to make sure it's actually using the right values. So density, velocity, and our viscosity is good. We're set here. So we're gonna go to methods and we're gonna change this the scheme to simple. That's how we want it to be solved. And we're gonna leave everything in second order. Then we're gonna go to our monitors and go to residuals. For our residuals, we're gonna increase this. We're gonna add 2 zeros. So all of these to increase, and it's gonna change this to 10 to the negative 5. And we should be okay. So we're gonna be okay. Or just want to make sure it's actually on there. All right. Then we're gonna go to our initialization, change to standard. We're gonna change our x velocity to, we're gonna go to inlet, sorry, and it's already set. And we're gonna make sure our y velocity is 0. This should be 0. And relative to cell zone is fine, and we're gonna initialize it. So it's initialized. Just want to make sure that it's actually initializing. I get kind of scared. Inlet, that's outlet, inlet, 0, initialize. All right, so it's doing that. We're just gonna make sure everything else is good. We did our residuals, method, controls are fine. Reference values, go back. Our inlet's fine. Reference frames, dynamic mesh, cell zones, we did everything there. Okay, everything seems to be looking good so far. So what we're gonna do is we're gonna go to run calculation. We're gonna go to number of iterations and we're gonna change this to 10,000. And everything else should be good to go. So we're gonna hit calculate. And you're gonna see it in the console. It's gonna run everything. And here's our residuals. See everything here. It's gonna go through as many iterations as it can. Trying to get as much data as possible. Then it's gonna be done. Is that calculation complete? Perfect. So we have everything here, scale residuals, and we have our mesh still. So that's good. What I'm going to do now is I'm going to do the velocity contour just to kind of show you how it's going to look here. And then we'll get into all of the hard data after. So now we're looking at the velocity with vectors and pressure contours around the flat plate. So back in Fluent, we're going to go to, where is it? It's a graphics contour. We're going to do velocity contour. This is going to be velocity magnitude. It's going to be, should just be here, save and display, close. As you can see, everything is here. You can see this developing boundary layer. And then we have that pressure gradient for the velocity, just ever so growing. What I'm going to do is I'm actually going to fit this back to screen. And I'm going to show you using the vector. So we have the contour there. I'm going to start a new vector. We're going to do velocity vector. And velocity, vectors of velocity, relative, make sure it's all good. We're going to do save and then do close. So you're going to see it here too. So you see it's developing here as well. But I'm going to show you guys it with both at the same time. So what I'm going to do is I'm going to create a scene. I'm going to call it, we're going to have both of these on there. So I'm going to call it velocity scene. Even at the velocity. I'm going to do save and display. You can't see anything, so I'm going to up the transparency a bit. Save and display. So you can see here, this is with them both on there. So this is it. And you don't need two, so you can kind of X one out and take a picture of this. You can zoom in and kind of see everything on the bottom, but this is fine. I'm also going to show you this in post. It's going to look a little different, but I'm going to show you the velocity contour and everything in post. What we can do is we can save this and X out of there. I'm going to, I can show you the pressure contour now as well on here. I was going to wait till post, but you can do it here too. So we're going to go to pressure contour and you have it here. So as you can see, it has pressure, static pressure. You can do save and display. You can do the dynamic pressure. You can do the absolute pressure. You can do the total pressure. You can kind of play around with those areas. So that's the pressure contour as well. And yeah, so that's that first half. So that was the velocity and pressure contours. I'm also going to show you that in post, so that's fine. But I'm also going to show you the velocity profiles at these two lines here with the boundary layer thickness at these locations. So what we're going to do is we're going to do it in post, and then I'm going to show you how to do it in Fluent. So I'm going to go here. I'm going to go to results. And in results, the first thing that we need to do is create two lines because we need to see how everything is looking. But I'm going to show you the velocity and pressure contours first, just so you can also see it in here. So we're going to go to contours. I'm going to do velocity contour. Can't spell. And then we're going to do all domains. We're going to do symmetry too. So it grabs everything. And then we're going to change our contours to, we can actually leave it on 10, or it was at 11, but actually for this one, you don't change it that much. This is for the, oh, this is actually showing pressure. Sorry. Velocity is what we want right now. And then you can see it still has that same pressure gradient there and growing boundary layer, but we can change this to like maybe 50 or actually like 20. And then you can kind of see it here, 30. Let me do 50. How did 50 look? You can see it here. But yeah, so I'm going to create another one because I just showed you the pressure contour. This is the velocity contour now, and then you can actually change the legend variable location. You can do horizontal. And then you can do apply. Or wait, I'm trying to get it to the top. Gonna make this bigger. We're gonna change how it is. Precision, fixed point, apply. There we go. This is a much better legend. And you can kind of zoom out to kind of compare everything here. And I'll leave the aspect as is. But yeah, I think this is good for the legend. But yeah, you can just update the legend. I just wanted to show you guys that real quick. But what I'm gonna do is, sorry, I'm gonna create another pressure. I'm gonna create another contour. I'm gonna show you the pressure contour in here. Pressure contour. So for this is pressure, same thing. So we're gonna change the symmetry to this one. We can really up because I'll show you if we put it like 30, it'll have it here. Wow, really showing it there. If you have it to like 100, it'll really show you everything. Yeah, pressure, all domains, symmetry 2. Yeah. Pressure not changing. This is the pressure contour. Oh, sorry, I had the velocity still checked. I was like, why is it showing it like that? So yeah, this is it here in pascals. And you can continue to up the amount of contours that it shows. Like if you went to 400, probably be insane. But you could really, really start to like see everything. And then you obviously the legend is changing with it too. But we'll leave it on here for now. But I'm going to take it off just so I can show you guys. Like I said, we're going to go back here. We're going to be doing part B. I'm going to show you the X plot and the Y plot, or the two X plots, sorry. We're going to go back to the post. We're going to go to location. Sorry, line. We're going to call this X35. And then we're going to have the point be, this is in meters, so make sure you do it in meters. So convert. So that's what I was talking about earlier when I changed this to centimeters. So yeah, and this line can also help you to tell you where you're at on in terms of the X and Y plane. So our height is is 50 centimeters, so that's where it is, and then here it's 0.35 is what we're using. So see the line there, and we're gonna do 100 samples. So this is basically just showing that we want it to be at an x coordinate of 35 centimeters, but we want the line to span all the way to the top of our surface, which is 50 centimeters high. We're gonna do apply, and you can see it's there. Then we're gonna do another line. So we're gonna go here, line x 75, and we're gonna do the same thing for this one. So 0.50, 0.75, 0.75, 110, 100 samples, apply. And then we're going to open up a chart. We're gonna do velocity profile. And then we're here. So now, yeah, XY line, data series. We're gonna add 2 of these. So the first one is gonna be X35 line. And then the location is X35. They're just calling it that for now. Oh wait, edit. Sorry, we didn't do number 2. I was jumping the gun. So we do X75. And then we're actually gonna make sure we change this. So our x-axis is gonna be the u velocity, y is gonna just be y. Line display, we don't really care about data, or this is gonna display both lines, sorry. Data series, we're just making sure everything is there. All right, so apply. And yeah, we can see clearly our 2 velocity profiles there. So yeah, that's this. And you can also do it in Fluent, but I just wanted to show you guys here, since we were in the solver, I wanted to show you guys part A and B in the solver, but everything else is gonna pretty much be done in Fluent. What I'm gonna show you is I'm gonna jump to part C and D, and then I'll go back to part B and A, or in Fluent, because you can do this stuff in Fluent too. So my mistake. So I didn't even peep that my headset had died. You see the RGB is back on now. But what I'm gonna do is I'm gonna quickly show y'all how to do part B also in Fluent, and then I'm gonna show y'all how to obtain the values for part C and D, which is the shear stress, the skin friction coefficient, and the drag coefficient. And I'm gonna kind of explain to y'all how y'all can tabulate it and compare the values and everything. So what y'all are gonna want to do is go back into Fluent. My fault. We're gonna just kind of start off here. So to get the velocity profile on here, you're gonna create surfaces. So you're gonna right click and you're gonna go to line and rake. Then we're gonna create our first surface. So we know that this is we know that this is the coordinate here. So we're just gonna name it that. So kind of same thing in the post. What you're gonna do is you're gonna have your X0 and X1 be where you're setting the line, and then you're gonna have your Y1 be the height of the surface that we have. So it's 50. And this is in meters, so 0.50 meters or 0.5 meters. So we're gonna create that as the first one. Close it, and we're gonna create a new one, and then do line and rake again. The same thing for the second point. I can't spell right now. Oh shoot. All right, so we have these here. So what you're gonna do is you're gonna go to XY plot, create new. You're gonna do velocity profile. You're gonna do velocity, velocity magnitude. You're gonna do not position on X order, and then you're gonna select both of these lines, right? And then for the x-axis, we're gonna do mesh, and we're gonna do y coordinates. So what this write to file means is if you were to write it, you would save the file. It would basically just be the data only. So that it would save in your computer. So you'd go to files, you would find it. So like, for example, if I wanted to do this, what I can actually do is I'll just open up Notepad because it's already open in my Notepad. I have that. You can see I did the shear stress and the skin friction. This is how you get the value. So you'd have your X or Y value on the left, and then you would have the corresponding shear stress value, skin friction coefficient, and velocity. Keep in mind the velocity is going to be in meters per second, and this should be in megapascals. or the shear stress, if I'm not mistaken. It'd be in megapascals. So what we're gonna do is go back to Fluent, and we're not writing it this time because we're just showing you the values. I'm just showing you guys the values, and then we would do save and plot, and then this is how the velocity profile would look. So you would save that, you like boom, okay, my velocity profile is done. Then you would go back to XY plot. So now we're gonna talk about the shear stress and the skin friction. So we're gonna do shear stress as a new plot, and then we're gonna do wall fluxes. We're gonna do wall shear stress, and we're gonna do it on the plate, and we're not gonna position it on the X. And we're gonna, oh no, we are gonna position it on the X, and we're gonna do order points. We're gonna do plate, save and plot. Boom, shear stress is done. So then you would create a new one, or you could edit that one if you don't care about having it. And then we're gonna do skin friction. And then this one is going to be wall fluxes again. And you're going to change this to skin friction coefficient. And you're going to do it on a plate once more. Keep that as direction vector. And then obviously if you're writing it to get the data, you're writing it. And then save and plot. And then this is the skin friction. And then now to get the drag coefficient, I need to search for it. Where is it? Actually, why is it giving me that error? I'm not sure why this error is in the console. But what we're going to do is we're going to go to report files. We're going to go to new. And I think because I've done this before, it's there, but we're going to go to drag coefficient. And then we're going to do, or actually, no, it should be report plots. Do report plots. New drag coefficient. Force report drag. We're going to do drag coefficient calculation on the plate. Drag coefficient, compute, and it's here. See, this is drag coefficient. You just copy that and you have that data, and you can hit OK. And then you would have it here in the report files. You would see them there. Or actually, you could have, what we were supposed to do is actually go into report definitions and then go new, force report, drag, and do it that way. But I did it the other way. So you would go here, would go to report definitions, new, force report, drag. It would pull up this menu. You could rename it, and you're going to click drag coefficient. You're going to hit zones, plate. Then you're good. Well, so to obtain some other information, what you could do is you could go here to forces, and then you could do plate, and you could print, and it could give you some other information, your viscous, coefficient pressures. You could also get some information on the surface integrals. You could compute, see what it spits out there and everything. And then pretty much, like I said, once you have that data from everything, you would just pretty much tabulate it all in Excel. And then like me, I did the report. I took the photos from everything and I tabulated all my data on here. And then I just, took pictures of everything and showed it in the report. But yeah, for the drag coefficient, I have the drag coefficient that we got from the computer in Fluent. And I actually calculated the drag coefficient using the formula, which is all found on here. And then I compared the two and did the percentage difference. I did the exact same thing for the boundary layer thickness. So that's what you're going to do. That's what he means, professor is going to say when he's saying compare to the theoretical ones. But yeah, this is pretty much the project in using Ansys. And yeah, I hope you guys enjoyed. This is project number 2.